we're going to work through what we need to understand all the different devices and stuff last time. All right, so this is chapter 5. No. It's chapter 4 in your book. Your book is kind of goofy in this. They introduce control volumes, and then they introduce the second law of thermodynamics. But that means that when they do control volumes, they can't really do it. And so then they have to come back and kind of like fix up stuff that they didn't go through the first time. So anyway, so now we're on chapter 4, introduce chapter 5. All right. So the basic idea, as I alluded to last time, is when you have an open system. Sorry, what is closed system? Let's review that. Closed system means what? Set mass, yeah. Sometimes a closed system is called a control mass. It means that you are in control of the mass. You define the system by its mass. Whereas a control volume is going to be defined by, you control the volume. You define a specific region of volume, and mass may or may not cross that boundary. Okay, so the mass doesn't have to stay inside the system. Okay. So that's what we want. I will just let you know, in physics, this is not a term I ever heard before reading engineering thermal books. We just call them open systems. But it's just a different, the physics presentation is a little different. Even though the material is the same, the points of emphasis are different. So kind of our idea is, we have some sort of a system. And the idea would be, you have, kind of archetypically, I guess, right? You just have many inputs, many outputs, and then you would define the volume, the control volume. Okay, so you would have material moving in, material leaving, and it doesn't have to just be one input and one output, although in most of the things we talk about, that is how it ends up. Because we mostly focus on the simplest things. Okay, so, well, because you can have mass enter and mass leave, we don't think about the mass. Instead, it's more useful to think about the rate of change of mass, or kind of instantaneous rate of change of mass. So let's think about that. Let's think about the mass of the control volume. That would be the mass on the inside of the volume. It's not a constant, right? It can change as you change dials and knobs and things. So because it's not a constant, let's actually focus, instead of that, let's focus on the rate of change. So this would be the rate of change of mass inside this volume. Now, the devices and systems we focus on are have defined inputs and outputs. Okay, so if we were talking about a literal cloud of gas, well then you can have all kinds of, it could basically leave anywhere on the surface, right? It could just fall out. But here, it's only going to occur at fixed entry. Okay, so hey Sydney. So you don't have to worry about, so the mass that's in the inside, right? This little bit of mass right here. This little bit of mass can't go anywhere because it's not near an exit or an entrance. Right? It's just in the middle. So in any given moment, all this little bit can do in a little split, a little jump is maybe move a little bit some direction, but it still stays within the control volume. Therefore, it cannot contribute to the rate of change of the mass on the inside. The only masses which can contribute to the rate of change of the mass on the inside, is the stuff that's concentrated near the entrances and exits. Okay? That's going to typically be the case. When we look at the rates of changes of things, there's really nothing happening on the interior. I mean, the little bit that's here maybe moves around, but it stays inside. So to figure out what's the change in the overall thing, you really just add up all of the effects at the edges. That's really where all the change happens. Okay? Because it's kind of like tree rings, right? When a tree grows, it grows on the edges. That's kind of the same idea. So, all right. So what I know though is then that the mass per unit time, well, I've got inputs, and I've got outputs. So the inputs are going to count with plus signs, and the outputs are going to count with minus contributions. So what we're going to do to build up the overall rate of change of mass of the control volume, we're going to add up all with plus signs, the mass flow rate for the inputs, minus the mass flow rates of the outputs. Is that okay? I'm saying a lot of words, but right. So the changes all are kind of concentrated on the edges. So we're going to say this is the sum over all the inlets m dot I for inlets, minus then we're going to have m dot E for, so these are inlets, these are exits, no, exits. You can call it whatever you want, but is the idea clear? This is very much like Kirchhoff's laws, his junction rule, right? The current in has to equal the current out. Same idea. Well, almost. It's going to be here in a minute. Is that okay? Well defined? Yes? And remember, the mass flow rate, we saw this before, the mass flow rate on a pipe, well, what was that? Mass flow rate, that's the mass per unit time. We wrote that as a density times a volume per unit time. So we wrote that as density at the inlet times the volume at the inlet. That's what something we had going back to Bernoulli's equation. Okay? And so there's a lot of ways we can rewrite this. Instead of density, what could we rewrite that with? What do we have that's equivalent to density? Mass over volume. Yeah, or specifically, what would you call it? Very specific. Which specific quantity is related to density? A very simple way. Remember, density is 1 over specific volume. Right? Density is mass per volume. Specific volume is volume per mass. Okay, so this is another way done. So this is the mass flow rate. This is the volume flow rate. Density here. Now, when we did Bernoulli's equation way back, densities were constant throughout, so you just have one number. Now, however, we're going to not just have a simple pipe. Now we're going to contemplate, a mixing chamber. You take liquid water, mix it with steam, right? So on one input, you might have one density. On another one, you might have another density. And if you know the temperature and pressure when it leaves, you'd have a third density. So you have to account for that. Thanks. What was the volume flow rate related to for a pipe? So if you had a cylinder, a pipe with an area A and a velocity flowed with a velocity, the water flowed with a velocity V, what was the formula for, how could you relate the volume flow rate to these parameters? We got units. Area times velocity, because it has to be per second. So a third way you could write this then would be the area of the inlet, if we're talking about inlets, times the velocity at each inlet, divided by the specific volume at the inlet. Okay? And I wrote for inlets, but you'd have all the same things for exits too. You remember doing all this stuff? Did a couple homeworks doing that? We're doing these equation things. Sydney, you okay? Asks to unmute. Oh, I have to ask you. Oh, I see. Okay, so the rate of change of mass in the control volume is concentrated at the edges, the boundary. In particular, you add all the positive contributions from the inputs, you subtract out all the negative contributions from the exits. Right. So we have those kinds of equations. So this is called the mass rate balance. Mass flow rate. Mass flow rate. Anyways, they say mass rate balance. I would call it mass flow rate balance. But we're also going to have an energy balance equation, right? So basically, it just says all the masses have to add up. However you do it. Okay. Okay. Great. Now, for us, we're going to study things in steady state. What is steady state going to mean for this situation? No. What would that tell you? This equals this. What does that tell you about this? Zero. It's not just constant, zero. That's what we're going to say. So we're going to run machines in steady state. We're running cycles, right? You run forever and ever and ever. We're not worried about the startup phase. Okay? So in that case, whatever's happening on the inside has settled down and is just remaining constant on the inside of your volume. You run it in steady state, it is constant here. You have mass crossing the boundary, but every time you add some mass, you pull some other out, right? So we're going to run things in steady state, basically always. So steady state for the mass rate balance is going to say that m dot for the control volume is 0, which means the sum of the inputs must equal the sum of the outputs, of the exits. Now it looks like Kirchhoff's junction rule. Current in equals current out. So, and if you think about it, Kirchhoff's laws work exactly the same. So, if you were thinking kind of microscopically, when somebody hooks up a battery, you look at a junction and a wire, there would be a term like this for current too. But the electrostatic or the electric forces are so strong that basically it reaches steady state just, I don't even know. I mean, you could be talking about 100,000th of a second or something insanely small. So this thing basically goes to zero insanely quickly, so you don't even talk about it in applications, but it would be there. Because it always takes a little time for the system to respond to changes, but you're talking about microseconds or something. I don't even know. I really don't even know. All right, this is going to be our key equation. Well, this whole thing. But this is going to be the stuff that we need to remember. Okay. Remember, because it'll be the same now. When we had Bernoulli's equation, fine. But then sometimes you couldn't quite solve the problem. And this was like the extra equation you needed to figure things out. Okay, so that's what happens. People forget that they have this at their disposal. And then they're like, oh, I don't have enough numbers. I can't figure out a problem. This is going to be this stuff, particularly this stuff, is going to be the one that kind of gives you that extra bit of information that maybe you didn't have. What if you only have one input and one output? Well, this becomes really simple. Mass in, m dot in is m dot out. Full stop, just done. So if you only have one input and one output, like a pipe, well, think about those devices. What were the devices we talked about last time? We had piping, we had a turbine, that was one in, one out. Boiler, one in, one out. Heat exchanger, that one depends on the details, right? That could be a little complicated. Mixing chamber had 2 in, 1 out, or it could be more complicated. What else? Nozzle, diffuser, those are 1 in, 1 out. Throttle, 1 in, 1 out. So most of the devices we have are 1 in, 1 out, and the m-dots just have to stay constant throughout the whole thing. There are a few devices which might be a little more complicated, but basically they're all, most of the ones we use are 1 in, 1 out. So it's simple. Okay? Everybody feel like they understand these ideas? Okay. Now, bring it to so tired. Should name that board 10. So it's really heavy. Heavy and broken. All right.
How you guys should do your math?
What would that? It's not that. It's not on the pole.
Is that the problem? Is that the problem?
It's just not a one. It's not a map. It's not a map. It's just, yeah. Okay. So that was the mass rate balance. I would call it mass flow rate balance. And then we're going to have an energy balance. Equation. Okay. All right. So, when in a closed system, it just sits right there in front of you, and there's stuff in it. And when you want to talk about the energy of that thing, what kind of energy do we say is inside that? What's the appropriate type of energy to talk about here? Internal energy, right? It's there in front of you. You're just talking about the energy that's in it. Fine. Why is that not appropriate for closed volumes? So the mass doesn't start in the system. You have to go from a world where the mass is outside to a world where the mass is now inside, or conversely, starts inside and you pull it out. So because you have to insert or extract the material, what type of energy measures that situation where you're adding something pushing it in or pulling it out. It's not just the internal energy, because you not only have to have stuff there, you have to make room for it. You have to push everything else out of the way. Not entropy, enthalpy, right? So the difference, remember the difference between internal energy and enthalpy is the energy that's in the thing, but also the energy needed to kind of make room for it in the universe. So we're going to be continually adding and subtracting bits of mass. That means that mass, as it goes in, it has to go in and push other stuff out of the way. So then when you're doing the bookkeeping, it shouldn't be that the energy balance equation is not going to be simply expressed in terms of, you can write it with internal energy, because you can always remember, enthalpy is the internal energy plus PV. So anything I can write using enthalpy, I could write with PV if I wanted to, right? Because it just go back and forth. What I'm saying is the appropriate quantity, though, the amount of energy that we really have to deal with isn't simply expressed in terms of internal energy. It's really more the enthalpy, because you also have to make room for stuff. So this is just the energy that's there in the container for a rigid fixed thing. This is the sound for, as you know, like when you open a can of soda, it makes room. It's that extra push to make room for things. All right. So let's think about this. So let's think about, and again, we could talk about the energy in something right now, but it could be changing as you adjust dials and knobs and things. So that's not really what we want to do. We want to set up the equation not for the energy in the control volume, but in the rate of change of energy in the control volume. How much is the energy inside changing per unit time, right? Because it's the same logic as we did for the mass flow rate. All right. So we're going to want to write down the rate of change of the energy of the control volume with respect to time, or E dot C. Okay. Now, what's the best way to say this? Yeah. All right, so, I think I'll just say it maybe without explanation. All right. Okay, so these are the same. What we want to do then is think about how are the ways that you have some volume, you have mass coming in, mass leaving. What else could be there? Well, you could have, maybe there's a boiler or fire underneath it, so there could be heat added, or maybe you have a turbine spinning, so you could extract work, or use the turbine, run it backwards, and stir the stuff up to give it energy, right? So the types of rates of change of energy are, you can have heat being added. So we're going to say heat in is positive, like we always do. We're going to say work out is positive, like we always do. So what we get is that the energy in the control volume, rate of change, well, there could be heat per second added, so that would be Q dot. Remember, dot just always means time derivative in this class. Minus the work you could have turbines and things, so you have positive work out. If you have work leaving the system, positive work out, or that translates into positive power. Right, this would be like mechanical power delivered. But okay, so if it's delivering power to your car, means that the control volume is losing, so you need that minus sign to make it work, right? So if it's becoming useful to someone else, then the system is losing. That's why you need the minus sign. Okay, what else could contribute to the energy rate of change? So far, it sounds just like we would do with a closed system, right? So what have we not accounted for here? What's different now that we didn't have an closed system?
Smart, whatever.
Well, or how about just the fact that there are inputs and outputs? Right? We have somehow that affects things, right? So again, kind of like, well, just like I was saying before, the energy that, there's a little droplet here, and maybe it wanders around a little bit, but as long as it stays inside the control volume, it doesn't contribute to the rate of change. So all of the changes caused by the flow of mass are concentrated at the boundary, at the inputs and outputs. So how much energy, when you have mass that goes in, say, how much energy does it give to the control volume? Well, it's going to give the enthalpies, right? So it's the internal energy plus the PV term. And then it also has potentially kinetic and potential energy. Usually it's negligible, but it could be there. So we're going to get plus, and let's think about this here. So, plus, so what I'm going to do, I'm going to write like this, summing over inputs, and enthalpy dot, right? Because everything's a time derivative here. Actually, you know what I'll do? I'll do this. Input plus kinetic energy. I'm going to rewrite this in a minute here. Okay, so don't, just give me a second. Plus potential energy. All of these, you can take a time derivative of. Okay, is it clear what I mean? So it's just the internal energy plus and the kinetic and potential energy that might be there. Usually these are numerically small, but okay, just for right now, assume it's there. All right, those are the inputs, so I'm adding, and then I have to subtract for the exits. So far. Is that okay? This isn't how we're going to leave it, but this is the energy balance equation. But we're going to write it in a better way here. All right. So basically, I don't want to write capital H, capital K. Yeah, I want to go to intensive quantities, so I want to use those instead of these. And make sure everybody has this. This is going to be a key equation block here that we use. Okay, so let's rewrite capital H in terms of lowercase h. How do you do that? So, yeah, or you can rewrite it. Okay, so we say this is enthalpy, this is specific enthalpy, and you do the mass times specific enthalpy, right? That's a familiar thing. Now, when you think about pipe flow, right? water droplets falling, going through a tube or something like that. All right? And you think about where things happen. So if I want to work out H dot, use the product rule, correct? So you say that's M dot times H plus what? M times H dot. Yeah? But here's the thing that happens. It's a question of length scales and time scales. So when you talk about the rate of change of mass through a whole pipe, there are kind of two ways that things can happen. You can think of it as a whole bunch of little droplets, mini droplets. M dot controls the number of droplets. H dot controls or tells you about what happens inside each separate droplet. And if you think about water flowing through a pipe, the thing that controls the amount of mass, or sorry, really, I guess what I'm saying is, inside each droplet, it equilibrates very quickly. So each droplet more or less is the same. The only thing that really contributes to the rate of change of the enthalpy is this first term. So very quickly, this can be dropped. Now, to justify that, you have to put numbers, but it's just true that inside a little droplet, you don't see, a droplet here pretty much looks like the droplets next to it. They all look about the same. So they're individually not really changing. So the overall rate of change of enthalpy just comes from adding more or less drops of water, not really the time change inside each individual drop. Okay? So it's really a statement that equilibrium seems to set in first on short distances and then grow to long distances. And so because the short distance, the stuff should average out, the intensive quantities become constant very quickly. It's only this term here that will become time dependent, potentially. Is that okay? Because we're going to make the same assumption for kinetic energy. So if I write out kinetic energy, right, so that'd be 1/2 mv squared. We're just going to, when we take a time derivative, we're going to make the same assumption, saying that the velocities aren't actually changing. One droplet pretty much has the same velocity as the one right next to it. So, and furthermore, it's more or less constant. Like it's not changing in time. All of the time dependence just comes from jamming in more or less droplets per unit time. So we're saying all of the time derivative here is basically carried by the mass flow rate. Plus, you have another term, but we're going to say that one doesn't contribute. Okay? And we're going to make the same assumption for potential energy. So that if you're talking about gravity, you would write that as mg h or z. Write it like that way. We're going to put a dot on that plus 0. So now you can kind of maybe see how we're going to write this. What we're going to do is rewrite all these time derivatives using this statement, using these ideas. And then what you see is every term is proportional to m dot. So you can pull it out. So our energy balance equation says that the energy of the control volume is Q minus W plus some of our inputs, M dot I, for the inputs, times H plus VI the velocity squared, not specific volume. Okay, minus, that was for inputs, minus the outputs, for exits. Oh, for exit. Okay, are you guys with me? See what I'm doing here? Now, oh, I forgot a dot. Dot. Now, in most problems, in most situations, you can drop kinetic and potential energy. And ultimately, the quantities you're looking up are enthalpies. I mean, it's the same kind of stuff we've been doing. It's just you want to pull it together this way rather than using the first law for closed systems. So it's the same as far as like the procedural steps you're going to have to do to solve a problem. Same thing, lay it out, identify what you have, identify what you want, go to the back of the book, get the numbers you need, given a certain pressure and temperature. All right. Another way that this can get rewritten, in fact, the book might even do another GC. Your book leaves it pretty much like this. Other books call this lowercase ke. Or it's the kinetic energy divided by mass. So they put a lowercase. So it's like a specific kinetic energy. And they'll call this lowercase p for a specific potential energy. It just means divide by mass like we always do. So if you see that somewhere, that's what's going on there. It's just this. All right, almost done. Just like when we talked about the mass flow rate, for the mass of the control volume, we're not interested in the startup slow down phase. We are interested in things which have been running for a while, in which case they have achieved what? What do we call that? When they settle down? Nope, steady state. It's not an equilibrium because we're adding heat and we're extracting work. It's not like that. If it's an equilibrium, it'd be more like you kind of just like you let it settle and you walked away forever, and you're not talking to it at all, right? Here, we are talking to it because we're extracting heat or work and heat and stuff, but we're running it in a way so that inside the control volume, nothing is changing. In particular, the energy in the control volume is constant, in which case this is zero. So our equation is going to be 0 equal, so this is steady state. So this is going to be 0, so that says Q minus W plus H. Right. Just don't want to miss any little bit. Oh, I forgot my dots. Okay. All right.
Should the second be, or well, yeah, should the be severe?
They do. They should. Thank you. Just it should be clear because of the absolute value that's the velocity, but because we have volume, volume flow rate, specific volume, and velocity, I like to put arrows so that it's really clear what's speed and what's volume or something.
So that's just the same equation you studied for the zero.
Yeah, same one. This is the one we use in this class. The other one is always true, but we're only going to talk about things in steady state. So you can always make that assumption.
How much more complex is it just like doing that for the initial startup of like something? Is that way more complicated?
Well, as you'll learn, it has to do with if you make things like when you're doing stuff in circuits where you have time-dependent circuits, it'd be that kind of a thing. So as long as you assume that you start it up kind of linearly or something kind of not too bad, it's the sort of thing that's not hard. Technically, it's just tedious because it's all going to become linear difference equations. You'd solve it. Probably you just put on mathematical. It wouldn't be bad. So probably you're going to get things like if this is linear, if the time dependence, if you add heat, constant heat in, or constant power in, this becomes a constant. It wouldn't be impossible. Yeah, it's going to be fine. Just tedious for when you have many inputs and outputs. So think about how many unknowns you have to solve for. For every input and output, you have to determine the mass flow rate and the state. So you need to know pressures, temperatures. It all gets tedious. You're going to do that all numerically in practice. For real materials, you're going to have to do it numerically because you're going to have to pull the data from a table. If for something simple like an ideal gas, it'd be much easier to do because all of a sudden it just becomes almost trivial. If you add heat in an irregular way, then it's going to be a circus. I mean, you're going to just put it on a computer and crank it out. It'll be a lot like doing those pandemic projects where you just put it there and it just chucks out the answer. You don't do it yourself. I would imagine, I haven't done lots of systems modeling, not really any systems modeling. I would imagine once you have a complicated system with enough devices that even though you maybe tweak one thing, the effects bleed through in a way that I bet there are some tricky, like it gets hard to expect what will happen. You're going to have all sorts of things. As I think about it, you're going to have all sorts of things like in chemistry class. You talk about reaction rates in chemistry. You remember doing that?
Yeah.
Right? You'd have like a limiting reaction that was the slow one, right? That was the one that the slowest one is the one that controlled more or less what happens. So what you could imagine is things like you turn on say you've got a mixing chamber, you're going to get a situation where it's designed so you have two inputs and one output. But then you can get situations where if one thing fills faster than the others, you can actually get backward flow. You could get weird oscillatory things for transient behavior. I don't know. I guess that would cause the machine to shudder and things, which is what happens. That's going to be caused by unexpected or undesired backflow. You're going to have once you're designing it to go this way, but in that startup phase, it kind of goes and overfills and then backflows and then underfills, oscillates back and forth, settles down, and then back to happen.
Look at jet engine turning on.
Yeah, could be. All right, this is our big equation. We're going to use this and that mass flow rate equation basically for every problem for the rest of the semester. So if you understand it, then it's fine. What's the tricky bit? As I look at it, so what was the first law for closed systems?
Q minus W equals change.
So if I was, the thing that would always make me, if I was in your situation, be a little nervous is the minus signs. Here you had Q and W together and positive delta U on the other side. Here's Q and W together but we have positive H's, we have mixed signs. So the key is gonna be to get the signs correct on the inputs. So you don't wanna get a minus and a plus. So I think it's easiest just to think about it as a volume and think about adding energy. So the inputs are gonna add energy to it, and the X's are gonna take energy away, and that's gonna fix the minus signs.
Are we gonna deal with kinetic and potential energy a lot in questions?
Most of the time you can ignore it, but there are some devices, like a diffuser or a nozzle, where they might, depending on the situation, depending on the numbers, blah, 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 they might be significant. Kinetic energy. Potential energy is only significant if you're talking about like a well. I don't think we're gonna have any situations where we worry about potential energy. Just for us, numerically, it just doesn't matter. But velocity can change in devices. All right. Let's take a 5-minute breather. That's a lot of new words. And then basically what we're gonna do is go through some devices. For each device, we're gonna write this equation down and just talk about. Most of the time, most of these are irrelevant and there are only gonna be a few that survive. But different devices have different ones which are surviving. So you gotta go through them and figure it out. Okay?
But for all of them, we're gonna be ignoring potential.
I think so. I can't think of a time when we won't, with all of our devices. That comes up if you're drilling a well, that's like, a mile deep or something, right? That's when you need, okay, that is a problem. I will also tell you, because I taught the tech thermo course, and I had never done like pipe loss and stuff. You account for friction basically with a fudge factor. The idea is if you had a stagnant column of water, there's no significant friction, viscosity, any of that sort of thing. So then the effects of friction should come in with the velocity portions because stationary water has no significant friction. So basically, you just add in a fudge factor, alpha here. And then there's like a friction coefficient, yeah. And now, the thing is, it's tricky because the number that you put there depends upon surface roughness, type of material, viscosity, blah, blah, blah. The speed of the velocity, it really depends upon the Reynolds number. So there's a whole kind of art to getting the right number, and there's complicated tables. But it depends, is it turbulent or laminar flow, all that. So basically, there's a fudge factor you put in there. And then also, if you have a bend, then you get extra contributions to the loss, not just the overall pipe thing. So for each bend, and it depends on the angle and the shape of the bend. And I think it's also a velocity squared term. It's just another term like this, but it's a different, you just tweak the coefficient again. You just keep tweaking that coefficient to adjust for that.
And then in the end, we just ignore it.
Well, we do, but no, it can be significant. In real systems, that can actually do it. They can affect things. We have some columns, the glass tubes that are about this tall. You fill them up, and there's like a hose, and you can like have a nozzle leaving, and the friction effects are as big as the non-friction effects. So it's like half the whole thing is friction dominated. So it's significant in that, but it depends upon the diameter of the pipe. So it's all like always, when you make it more and more real, it's not that each little bit isn't hard. It's the layers. All right, 5-minute break. Okay, so we're going to go through. We're going to talk about different devices. We're going to use our equations. We have our mass flow rate balance equation. We have our energy rate balance equation. We're going to run things in steady state, so don't worry about that. And basically then we're going to go through different devices, different components, work through what are the reasonable assumptions you can make. If you have a nozzle or a diffuser or a turbine or a boiler or this or that, blah, blah, blah. Okay, What can you assume about them? And then we're going to build up, hopefully like I was trying to indicate, for each device, you're going to have a standard set of assumptions, what you can make. And then when you talk about a real cycle that's made up of like 4 components, you just put all those give you your different assumptions you need to look up numbers from the back of the table. Once you get the numbers from the table, you can get the heat and work for the whole cycle, evaluate it. That's how the game will be played. So right now we need to understand the separate pieces, and then we'll have to practice pulling it together. Is what we do. So let's start with pretty much the simplest ones. Nozzles and diffuser. So a nozzle and a diffuser. If you take a nozzle and you hook it in backwards, it is a diffuser. Right? So a nozzle will be like this. You know, if I have flow going in, like that, and a diffuser. Now, this is one of the drawbacks of learning this stuff from a physicist. There are different standards for how to draw these things. But not every book uses the same standard. So there are a couple different ways that people do this. So you should be aware, whatever book you have is going to have a standard way. It'll always draw the nozzles in a certain way. I think, yeah, your book is kind of sloppy. But there's, yeah, this is how your book does it. I think nozzles and diffusers are always the same. It's turbines and pumps and stuff that I think they can be drawn in different, or heat exchangers and things can be drawn in different ways in different books. I don't know. That's an engineering thing. I'm just going to go with what the book has. But this is how we have. So fluid comes in. What's happening here? Like think about a garden hose. Pinches down. What's changing as it goes through the nozzle? Area is decreasing. All right, let's go through the whole analysis just to remind ourselves how it works. Our key equations are, we have the mass equation. We're running it in steady state. So we have 0 equals the sum of m dot in minus sum of m dot out, right? That's our mass flow rate equation. And it's in steady state, so they're the same. How many inputs do I have? 1. How many outputs do I have? Right, so I just end up with m dot in equals m dot out. That will happen whenever we have just one input, one output. Okay, that simplifies our life. And then, how can we write m dot? We talked about it. How do you rewrite? You were talking about areas and velocities and things. How do I do that? Right, so I can write this as the density times volume flow rate, or 1 over specific volume input times the area input times the velocity of the input must equal 1 over specific volume of the exit times the area of the exit times the velocity of the exit. Okay, now, in the normal, if I'm thinking about like water through a garden hose, the density doesn't really change much. Or even, to be basically, yes, there is specific volume stuff happening, but it doesn't, for our intuitions anyway, we're going to assume that these don't dominate the effect. That tends to be a good assumption. So now, tell me what's happening. Goes through, what's the shrinking here? What does that change in this equation?
Area.
Changes the area first, and then, so if I shrink, if I shrink the exit area, then the rest of the variables have to adjust. And that means particular, you would expect typically that if the area decreases, the velocity increases. So if one goes down, the other goes up. Now, in reality, though, it's a little more complicated than that because you could also try to compensate by adjusting the specific volume. And it all has to do with knowing the temperature and pressure at the input and input, exit. But the intuition is still there. Right? Very good. So we learned that the velocity of the exit tends to be less than the velocity of the input for a nozzle. And what about a diffuser? It's just reversed, right? Then it's greater than, it goes faster at a diffuser.
Should it be the exit be greater than the initial, or should it be smaller?
On a diffuser, the area grows. Oh, wait, hold on. Maybe it says wrong. Oh, thank you. I just did that to make you feel better. Say it again. The area shrinks, so the velocity increases on a nozzle. On a diffuser, it goes the other way. Okay. All right. Let's talk about the energy equation. The energy equation is going to say, well, all right, we're going to run it in steady state, so I get 0. You have, okay, let's say we have Q dot, that's the heat transfer rate, minus W dot, plus the sum of M I dot times H I plus, I'm just going to write K E I plus P E I minus sum on E M dot H plus K P E E. Phew. Big old equation. Oh, just a comment. Your book puts a CV here for control volume. It's obvious. I never label it, but that's what it is. All right. Control volume E. All right. Now, a nozzle is a passive device. Right? That's why they're so cheap. You just taper something. So there's no turbine spinning, or there's no work being done. There's no electrical work going in. It's a dumb device, right? So we know immediately. So what are the assumptions we can make? No work. Yeah. The work is 0. How big is a nozzle?
Make it big as you want.
Okay, but in real life.
Is there one on the sink face?
Okay. Is it 1,000 feet deep, like a deep oil well, a single nozzle that goes all the way to the bottom of the ocean? No. So the potential energy is going to be negligible. You just don't worry about it. The change in potential energy is negligible. You can just drop those terms relative to everything else in the problem. Okay? And how many inputs do we have? How many outputs do we have? And now from this equation, I know that the mass flow rates have to be the same. So I can write this as following. I can say 0 equals Q dot CV over M dot plus H in plus K E in minus H exit K minus K E exit. right? They have the same mass flow rate. It's the same m dot. So you can just regroup that. And that happens all the time in these things. Q dot over m dot. What is that? If you were a make some joke about hospital. Use L'Hopital's rule. What would that equal? Or what does L'Hopital's rule connect that to? That's nothing other than Q over M. Ratio of the functions is equal to the ratio of the derivative of the functions. Well, what's Q over M? Specific amount of heat, not the specific, remember? Yeah. All right, so that's little q. Control. So if I write it that way, all the time dependence goes away. Really, that's always going to happen for us. All of the real time dependence is just in this m dot thing, which is just some overall factor. Everything else is just going to move. The interesting stuff is all just in the intensive things, which are constants. Okay, so we get that. Now, for many situations, the heat is basically zero. Like when water goes through a garden hose, there's not really significant heat radiating through the nozzle. So for many situations, you set this to zero. So usually this is small. All right, let's do a question. All right, we're going to have steam entering through a converging, diverging nozzle. So that's like a nozzle connected to a diffuser. So it converges and then spreads out. There's a picture I'll show you. All right. There's some temperature and pressure at the input and some velocity at the input. The steam goes through the nozzle. There's negligible heat transfer. What does that tell you? You can assume. Q is zero. Yeah. And no significant change in potential energy. Well, that's always going to be. At the exit, you're going to be given a pressure and a velocity, and you know the mass flow rate. They want you to determine the exit area of the nozzle in meters squared. Okay. So I'm going to draw a picture of it so you can see. So I'm going to draw the picture, and I'll lower the screen, and then you can see the problem. So I'll put it on the overhead. The picture is going to look like this. I'll put the problem on the board. So the picture is like this. So we have something like this, like that. I don't know. So there's some area at different points. So I don't know the sizes of things. What we are told is the following. We're told that m dot is 2 kilograms per second. We're told that P1 is 40 bar. T1 is 400 degrees Celsius. The velocity at state 1 is 10 meters per second. It's flowing to the right. There's insulation, so we're told that Q is 0. So obviously it don't work. And we're told at the exit, P2 is equal to 15 bar. And we are told the velocity at state 2 is 665 meters per second. And we are asked to determine, we want the exit area. Actually, I don't even know that. I don't need that. I think I've got all the numbers there anyway. I don't think I need to put it on the overhead. Okay? So find the exit area.
That's 6.65.
655 meters per second. So it's moving fast. Yeah. Why, if you're writing a problem, why would you crank up the velocity? Well, it means you probably don't want to ignore the kinetic energy terms. If you're talking about a lazy river, drop it. It doesn't matter. If, you know, everyday kind of velocities just don't rate. They're like 1 part in 1,000 in terms of the contribution. But at high speeds, all of a sudden, it's significant. All right. We want the exit area. That's what we have to do. All right, Alex, you and Billy work together. Let's work together by tables. How are you going to do this? How many formulas involve area at all? Yeah. So which one? Yeah, the mass flow rate equation. So that's your hint. Use that equation to figure it out.
Is not the change in mass in and the change in mass out. Or are they both?
Because there's one input and one output, they're equal. Sorry, guys. So let me recap because I stopped recording for a second. So we want the specific volume at state 2 so that we can get the area at state 2. We only know one state variable, one property. So to do this, the way we're going to work it is we're going to first figure out the enthalpy for state 1 and then use the energy equation to determine to get enthalpy at state 2. Once you do that, you will know a pressure and you will know an enthalpy. You can use that maybe and interpolate to find the specific volume at state 2.
Would the temperature really change that much from going in the thing to going out?
Well, the velocity has gone from 10 meters per second, 20 miles an hour, to 1,000 or more than that, like 1,400 miles an hour. So the velocity change is extreme, so I don't have an intuition at that point. We're not talking about lazy river. Right? This is extreme. So the answer is I can't say. And it is also compressible because it's a vapor, it's a gas. So a lot of your intuitions, you're thinking about the garden hose now. Well, that isn't such a good. Yeah, you can't use garden hose. Figure this one out. So that's your idea, or that's the plan. Use those other numbers to get H1. Use the energy equation to get H2. Once you have H2, third, use P2 and H2, maybe with interpolation, to get specific volume 2. Because you have to have 2 numbers to get everything else, always. So this is how we're going to get our 2 numbers so that we can figure out the specific volume at state 2. All right. Let's have a go. All right. So let's go through these steps. First, we're going to determine H1 from the tables. So let's do that. We'll just do it over here. I know P1 and T1. That's just one of the entries, right? So you go to the tables, go to the steam table. And what we find in the steam tables is that at 40 bar and 400 degrees Celsius, what do we get for H1? What do you get?
3,213.6.
13.6. And the units on that would be kilojoules per kilogram. Yeah? Which would be, since we're wanting to get things out in meters, we want to get everything working in normal kind of metric units, not kilojoules. We want to get it to joules, or that's one way to do it. So I'm going to write this as 3.216, 2136, whatever, times 10 to the 6 joules per kilogram.
6.
Well, I want to work towards joules. Actually, you know, we'll leave it. Let's just leave it as kilojoules so we can do the data table. We'll do that part next. So write it at, let's just leave it like that. Leave it like that. Sorry, I jumped the gun. And, okay. What are the units? If I do velocity in meters per second, then kinetic energy is going to come out in joules, right? Normal, like physics 1 stuff. But the enthalpy is in kilojoules. So that means I need to get this term into kilojoules, I need to divide the number by 1,000. Yeah. Well, it's not kilometers per second. It's not. Because kilometers per second would be, that's going to be like kilometer times a kilometer, right? Because it's velocity squared. So it's not the same as working. It's not like you're just working in kilometers. It really is just a factor of 1,000 is what you need. So, all right. So what I'm going to get then from using the energy equation is that H2 equals H1, 3213.6 kilojoules per kilogram, yeah, plus V1 squared, I mean, that's going to be pretty much negligible, minus V2 squared. But when I use kilojoules on this, I need an extra factor, I need to divide by 1,000 here. So if I write it out literally, like without making any assumptions, what I'm going to get is 10 squared over 2 minus 665 squared over 2, and the units on this term are joules per kilogram. Right, so far, I haven't assumed I haven't made a mistake. But you got to watch the labels, right? Everybody clear why I can't just add these together? These are in kilojoules. These are in joules per kilogram. You know, joules. So if I want kilojoules, what I have to do is I can use kilojoules, but then I get an extra factor of 1 over 1,000 to do that. Okay. Now, here's the deal. Most of the time, kinetic energy doesn't matter, and so most of the time you don't have to deal with this stupid factor of 1,000. But if velocity is important, you have this factor every single time. So this is a weird thing. Usually we say, oh, I just use the normal units, blah, 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 and it just works out. If we were doing everything in joules, that would be correct. But because the energy, the internal energies and enthalpies are in kilojoules, it's more complicated than it usually is. You have to watch, and you always get this factor here. And it's even more fun when you're doing barbaric units. Okay, but you have something similar to that. All right, so now we can combine all these things. What do you get for this enthalpy? When you put it all together, what do you get? 2992 kilojoules per kilogram. And you go to your book, and that's pretty close to one of the entries in there, right? So they were nice. So this example was chosen so that it came out nice. That's why they chose that 665 number for the velocity. So what do you get for, this is in the tables, you know the pressure is 15 bar, you have this enthalpy, what do you get for the specific volume?
0.167.
And that would be meters cubed per kilogram, yeah. You got lucky that's on the table. Normally you have to interpolate. Should be more a little bit of fun. And once you have that, you go back to our formula. And for the area, we get, it was 4.89 times 10 to the negative 4 meters squared. So, okay. All right. That is how you do this. Okay? It's the same skills we've been doing. It's just pulling it together in a different way and using these extra equations to do it. When we do a turbine, it's going to be the same, except you have, instead of being equal to 0, you have it equals to the work. It's the same set of assumptions. If you do a boiler, you'll assume the kinetic energy doesn't matter. You'll assume that the work is 0, but you keep the heat. So for each device, it's the same basic idea. You just have different assumptions to what you can keep, what you can ignore, and you just got to know it and think your way through it, and then you can design your own heating and air conditioning system. It's really that simple.
It's not those.
Well, it's not like to run the numbers to know like what pressure you need or what temperature you need and things like that. It's really not that hard. But I don't know about designing like what size shape nozzle. That's harder to do. All right, let's stop there. So